Students, today I'll be talking about VLSI. What does VLSI stand for? VLSI stands for Very Large Scale Integrated Circuits. So, if you consider the development of VLSI over a period, it started all in 1940 when Bell Laboratories started making PN junction, and Russell O'Hull was responsible for it. And in 1948, there was a breakthrough when Shockley, Bardeen, Brighton, Bell Laboratories uh, produced the first transistor. So in 1956, all of them shared Nobel Prize. And in 1950s, purification of silicon was done to a greater level. And in 1958, Seymour Cray made the first transistorized computer CDC 1604. In 1959, you have Jack Claire Kilby of Texas Instruments making integrated circuits with 10 components on a chip of 9 mm square. That was a great advancement at that period. And later, Robert Norton Noyes improved the integrated circuit, and in 1968, Noyes Gordon E. Moore found Intel, and in 1971, the first microprocessor 4004 was manufactured by Intel on a 9 mm square chip. It had 2300 transistors on it. Since then, there is no look back for the integrated circuits, and today we have a technology with a gate length equal to 7 nanometer. It's a big leap for IC industry, and we can see here the change in the size of the transistor taking place over a period of many years, right from 1970 to 2000. So we see here the improvement in the size of the MOSFET also reduce the switching time and also power consumption. And in this figure, we can see the comparison of a transistor with respect to rabies virus, both at the same scale. So you can imagine how small was uh, the transistor when the comparison was made. Coming to the challenges here, when we make an IC, we have several challenges to face. They are classified as microscopic issues and macroscopic issues. The microscopic issues are the ultra high speeds of the devices, power dissipation, and the supply rail drop, growing importance of interconnect of these chips or the devices within the chip, noise, crosstalk, irreliability, manufacturability, clock distribution. So all these things plays an important role while we design the chip. And when we do the marketing of the chips, we need to consider the time to market. How much time is it required to design, make a chip, and then send it to the market after testing? So we need to consider the complexity, how many millions of gates we can accommodate, and what are the different levels of abstractions, and how do we do the testing, whether we can use the same chip design again and again, whether we can combine multiple systems on a single chip, whether we can combine multiple tools which are used to design the IC into one platform. All these things are challenges when we face outside the domain of uh, chip making. So here we see the changes that are happening year to year, and how it is bringing change in the size of the gate, and then the frequency of operation, the cost size, and the staff required to do the designing. So there is a big change that is happening over years. Coming to integrated circuits, we all know that integrated circuits are nothing but the digital logic or a logic circuit which are implemented on a single chip. The chip, all of you know that, is made up of silicon. So the first is integration is small scale integration, and in that you have only 10 gates or even less than that. The next level is medium scale integrated circuits, which has 10 to 100 gates in it. Large scale integrated circuit has 10 raised to 4 gates in it. And very large scale integrated circuits contain more than 10 raised to 4 gates. That means more than 10,000 gates in a single chip. So improvements in manufacturing is leading to smaller transistor sizes and also higher speed of operation, consuming lesser power. So we are able to manufacture now millions of gates in a single chip, and the number of transistors doubles every 18 months or so. So this was foreseen by Gordon Moore, and hence this is also, the statement is also called as Moore's law. So there are varieties of logic families which we use in implementing the circuit. They are TTL logic, which represents transistor logic; CMOS, which represents complementary metal oxide semiconductor; ECL, emitter coupled logic; gallium arsenide logic, and so on. In this figure, we see here this round circle type of structure represents the wafer, and in each rectangle or square you have one chip, and you can imagine the size of this wafer, it's around 20 centimeters, and size of each chip is 1.5 centimeter into 1.5 centimeter. And then after that, when it is packed, it looks from the side view in this fashion, where these represents the pins or the leads. Coming to Moore's law, Moore, who was working for Intel or who started Intel in 1965, predicted that every year or in every 18 months, you can expect the number of devices would double. So this was a kind of prediction, and which became true. So almost every 1.5 years, the number of gates within a chip doubled, and that is shown here in this diagram or in this graph. And you can also see how each microcontroller or microprocessor developed over different years. So right from 4004 microprocessor chip to 8080, 8086, 286, 386 processors, and now we are in the age of Pentium 4 processor and multiprocessors. So this is also a comparison of the size of the chips in the graphical manner. So we have now the size of the wafer also varying, that is, it has reached a size of 200 to 300 diameter, and the material what we had using for making chips are also being changed, and the film size is in the range of 10 raised to 9, 10 raised to minus 9 meters, that is nanometers. Here in this picture you can see wafers of different sizes, the bigger one being 200 diameter wafer, the smaller one is 51 diameter. So in this figure you can see Intel 4004 microprocessor. The internal structures are also seen in this photograph, and this is Intel Pentium 4 microprocessor. It's very complicated as it appears here, and the size, how it changed, the size of the die, how it changed over multiple years is shown in this diagram. It's almost a change of more than 10 times in a gap of year from 1970 to 2010. So die size grows by 14% to satisfy Moore's law. So as we go on scaling, reducing the size of the transistors, we observe the frequency of operation also increases. So what we see here in this graph is frequency of operation to that represents the time taken to complete a small task in any processor. So here it is ranging from 0.1 megahertz to 10,000 megahertz in this graph. So we have even more advanced, but more advances are now made with respect to using multiple processors. So very large scale integration involves design of extremely small circuits, and it contains millions of transistors, and applications are various. Most of them are electronic logic devices. As we go on coming to the end of Moore's law, the scientists have come up with a better idea of incorporating multiple chips over each other so that they can reduce the size of the chip. So here in three-dimensional VLSI, what we do is, instead of having different chips, or instead of having different systems on a single chip in a two-dimensional pattern, we go for three-dimensional pattern wherein we can stack multiple chips one over the other and do the interconnections with each other. By doing this, we can have multiple advantages. So the connections are done with the help of micro bump, TSV, and the bump in this 3D IC. The down portion, what you see is package or substrate or PCB. So the advantages of 3D VLSI are, first of all, we can reduce the noise that appear across the interconnects when we have a chip of this nature. If the interconnection length is more, the noise effect is also more. The crosstalk noise represents the interference between the interconnects. Electromagnetic interference represents the influence of electromagnetic fields around the interconnects. So here in 3D chips, you have shorter interconnects and fewer pins. Therefore, the speed will improve and the delay also reduces as resistance and capacitance of the interconnections reduce. Next, the power also is found to reduce. Why? Because power, dynamic power is proportional to the frequency of operation, like capacitance of the wires or interconnections, or the load capacitance within the chip, and V represents the voltage, maximum voltage, that is power supply voltage. So when we employ 3D VLSI, we find that even the power dissipation also gets reduced. And if in a capacitive circuit, the power dissipation is given by P is equal to FC V square, and in a resistive circuit, power dissipation is given by voltage square by resistance. So naturally, resistance, the power dissipation is found to reduce in case of interconnects in 3D VLSIs. So here the packaging also reduces the size of the 3D IC. The weight also reduces, and you get an improvement of 40 to 50 times reduction. The challenges of 3D ICs are thermal management. How are we going to avoid the heat around the 3D ICs? So we have to come out with better packaging, as we have to manage higher density circuits within a smaller package in 3D ICs. So we need to draw the layouts properly, so that the heat gets absorbed by the cooling packages which are provided, and you need to also provide specialized cooling techniques which can let out the heat outside these 3D ICs. So there are a lot of changes that are happening in 3D ICs, and it's quite challenging. That's the introduction for VLSI. I hope you all enjoyed it. Thank you.